Welcome to the third part of week 6. In the previous lecture, I have explained how to calculate things like the interspike interval distribution, how to calculate the survivor function. We'll now use these notions to look at the likelihood of an observed spike train. Suppose an experimentalist has injected a signal into a neuron, and he observed spike times. Suppose a first spike at time t1, a second time at time t2, a third spike at time t3. The upper index indicates the firing times. Firing times are events, and the spike train as a whole is a sequence of events represented as a sequence of delta pulses. Now, you as a modeler have a model. You inject the same current and you add escape noise so that your model also generates spikes. And now you ask, what's the likelihood that this spike train with the firing times at T1, T2, and T3 could have been generated by your model? Now, here's the answer. You can write down the likelihood. Now, of course, this needs some explanation. That's what I will do now. So here again, my sequence of spikes. We have seen in part 2 that we can discuss the question, what's the likelihood that a neuron would survive a certain interval from T1 to T2 without firing? So what's the probability to survive? Well, it's given by the survival function. At each moment, the neuron has a certain rate of firing. At this moment, say t, it has a certain rate rho of t. But we observed that it did not fire. The probability to survive without firing decays exponentially. And it doesn't fire in the whole interval from T1 to T2. So we integrate this instantaneous rate from T1 to T2. And then again, the neuron should stay silent. It should survive from T2 to T3 without firing. T2 is this firing time here. T3 is the next firing time. Firing times are the upper index. So this must be an upper index here and there. But then the neuron actually has to fire at time T2. Well, it does so with a firing intensity rho of t evaluated at time T2. Similarly, it has to fire here at T3. And then it doesn't fire again between T3 and T, capital T. So it's again times e to the minus from T3 to the end of the measurement period rho of T prime dt prime. And it also stays silent at the beginning. So I have e to the minus 0 to T1 rho of T prime dt prime. And it did fire at time T1. So the likelihood that within this period from 0 to T, we would observe just 3 spikes at times T1, T2, and T3 is therefore this. Now, working with these instantaneous rates, stochastic intensities with escape rates in continuous time, sometimes causes problems. It's hard to imagine this. And sometimes it's easier to think in discrete time. Moreover, any computer implementation has to happen in discrete time. So let's introduce some discrete time bins. So I introduce my time bins like this. And let's look at this time bin at this moment of time here. I call this TK. Now let's look at this moment here. This would be TK plus 1. The lower index K is an index of the time bin. The upper index F is an index for the firing times. Now let's look at the probability to survive this interval delta, the time step delta, without firing. The probability to be silent in this interval delta is this given by the survivor function. I integrate from tk to tk plus 1, rho of t prime dt prime. Now suppose that this is the time dependence of my function rho of t, which I need to evaluate at these different moments in time. This would be at tk, this would be at tk plus 1. And you see that it changes only slowly. The difference between the value here and the value here is marginal. Whereas at some other times, it might have a completely different value. So if I say that rho changes little in a small time step, then I can approximate this by the following expression. I just evaluate at time tk, and then I multiply with the duration of this integral. So, the probability to stay silent in these different time steps here, time steps, time moments, k prime, would be you need to stay silent in one time step, say rho of tk prime times delta, and then you have to stay silent again in the next time step. Tk double prime times delta would be the next time step. I have exponentials here. The product of exponentials can be written as a sum. Rho of tk prime, I sum over all k prime times delta. Now I sum over all tk primes that lie in between T2 and T3. I do something similar for the interval from T3 to capital T for this interval and for this interval here. So far for the periods where the neuron does not fire. But then there are these moments when the neuron does fire. For example, in this interval here. Well, the probability to fire is 1 minus the probability of staying silent. So this is 1 minus e to the minus rho of tk times delta in the approximation I made here. And I have to add all these different moments P of t f delta for all the moments where I have firing. Product over all firing times. This is the sum of all bins where the neuron stays silent. So this is the discrete time construction of a likelihood. Now let's ask the following question. What happens if I make this bin size delta smaller and smaller. So, for this bin size here, I said I have a certain probability, which is 1 minus e to the rho of tk times delta. Now, the Taylor expansion of e to the x is something like 1 plus x plus a term x squared and so forth. So if x is small, and that's the case, I take delta very small, so this is going to be very small. I can use this Taylor expansion and I arrive at rho of tk times delta, which becomes valid if delta gets very small. So now consider the transition from time steps of duration delta to time steps of half the size, delta prime equals delta over 2. Well, now I had a certain probability to fire in that time step. I must have a smaller probability to fire in the short time step, because the total duration to fire between here and there, the total probability to fire between here and there should not change. And that's true for this firing probability that is proportional to the step size delta, valid in the limit delta to 0. Now, all the survival terms that I have for the silent periods have the form e to the minus sum over k prime rho of t k prime times delta. If I take the limit of delta to 0, then this transforms back into our known integral rho of t prime dt prime. And the intervals go over all these silent periods from a first firing time to the next firing time. Now, if we write down the likelihood in discrete time, for a situation with exactly n spikes, then we would have the product over all these different firing times, f equal 1 to n, rho evaluated at tf times delta, multiplied with the survivor function going from tf to tf plus 1 rho of t prime dt prime. And the product is over all these different firing times. Plus I should add the intervals at the beginning and at the end. I don't have the space to do so, and it's not important for the argument that I'm going to make. Now what you see is that in this discrete time formulation of the likelihood, I have this term delta. I have a term delta for each firing time. So overall, I can move that in front. The script L for the discrete time likelihood is related with a factor delta to the n, where delta is the step size, to the continuous time likelihood. Our continuous time likelihood is really a density, and you have to integrate it n times to get a quantity that's related to a probability. So it's a this continuous time likelihood is an n-fold density. And here it's again. Our density, this is the first interval. Then I have my spike. This is the second interval. Then I have my spike, and so forth until I have the last interval. I can rewrite this in a slightly different form. We see that this integral here goes up to t1, but the next integral starts at t1, it goes up to t2. The next integral would start at t2, go up to t3, and so forth until the final one, which goes from tn to capital T. So all these terms give rise to one single integral over the whole period, the whole measurement interval from 0 to t. The moments of firing for n spikes, f equal 1 to n, I have n instantaneous firing rates. Now sometimes the likelihood is not written in this form, but it's transformed to a log likelihood. So if I take the logarithm of this term L, of this likelihood L, well, the logarithm of the exponential is just the term in the argument of the exponential. Then I have a product. The logarithm of a product gives a sum. In fact, I have many products that turn into a sum over all spikes rho of Tf. Thus, the likelihood can be rewritten as a log likelihood, and the two formulations are completely equivalent. I can also go back from the log likelihood to the likelihood. The reason for considering the log likelihood is simple. It looks nicer if you have sums compared to products. Let me summarize this. An integrated fire model with escape noise can be seen as a stochastic spike generator, can be seen as a generative model, a model that can generate spike trains. If you have observed a spike train, we can ask, what would be the likelihood that this spike train could have been generated by my model? And the nice thing is, we can write down, we can calculate this likelihood. Now a model, such as the integrated fire model, will have parameters, for example, the threshold. We are able to calculate this likelihood for different values of the threshold. And as we will see next week, this is the basis for optimizing parameters of such a neuron model.